Good day, everyone. All right, we're working in section 13.3 still with trigonometric identities. In the previous two videos that I've asked you to watch, you've learned about using a cosine double angle identity and a sine double angle identity. And what's going to happen in this video is we're going to learn how to apply those. You're going to use double angle identities in order to calculate the values of sine 2x, cosine 2x, and tangent 2x. Now, these are the identities that we proved or derived, if you will, in the previous videos that we've learned. It's very smart during this video to have these written down in front of you. So either make sure you just write it down on a separate sheet of paper that you can keep referencing, or if you happen to have a copy of the formula booklet, these are in there, have that nearby so that you can reference it, because there are going to be several times where I'm going to ask you to find cosine of 2 theta, for instance, and we'll have to determine not only how do you do that, but which of the three versions of the cosine double angle identity do we want to use. All right, so write these down, and while we're at it, in the goal, I said we're going to be able to calculate sine 2x, cosine 2x, and tangent 2x, and we did not learn a formula for a tangent, the double angle identity for a tangent. So let's go ahead and write that down, because we can take care of that very simply. You know the identity that the tangent of theta equals sine of theta over cosine theta. Well, that applies to double angles as well. The tangent of 2 theta is equal to the sine of 2 theta over the cosine of 2 theta. So with those identities / formulas in hand, let's go ahead and see how we can calculate the trig values of double angles. These are very fun problems that we're about to embark on here. I want to read it for you, and I'll explain the premise of what we're trying to accomplish. Given that the cosine of x equals -3/4, and that 180 degrees is less than x is less than or equal to 360 degrees, we're going to calculate the values of cosine of 2x, sine of 2x, and the tangent of 2x. All right. Now, in this problem, we don't know what the angle x is we're working with. So it would be impossible to plug in the value of x and use our calculators, for instance, to find out what the cosine of twice that angle is. But we do know what the cosine of that angle is, and we have a good idea of where it is on the unit circle. Anytime you know the sine, cosine, or tangent of an angle, and you know which quadrant that angle is located in, you're able to calculate a whole lot of other trig values for that particular angle. Now, the first thing that we're going to do before we actually try to use formulas to calculate these three values here is we're going to draw a picture of where this angle is on a coordinate plane. I'm not actually going to try to fit it on a unit circle. It wouldn't make a lot of sense for what we're trying to do right here, but I am going to put it in a coordinate plane nonetheless, because I want to know which quadrant this angle is. Now, you know that if a value of a cosine is negative, that the angle that gives you that cosine can either be in the second or third quadrants, right? So how do I know whether this angle x is in the second or third quadrant? That makes a really big difference. Well, I told you that x is between 180 degrees and 360 degrees. So that means it's between here and here. And between those two quadrants, only one of those would have negative cosine values, and that's the third quadrant. And so what I'm going to do is I'm going to make that angle in the third quadrant. Let's just go ahead and say that this is the terminal side of that angle x. All right, so this could be x right there. And then, using the terminal side of that angle, I'm going to make a right triangle by connecting it to the x-axis. And we're saying that the cosine of x is equal to -3/4. Now, let's go back to your right triangle trigonometry. You know that the cosine is a ratio between the adjacent leg and the hypotenuse of a right triangle. So we aren't going to say that the adjacent leg is -3. The negative part is taken care of by the fact that this triangle is on the left side of the y-axis. But what we're going to do is we're going to say the leg adjacent to that angle right here is 3, and the hypotenuse is 4. Makes sense? Cosine of x equals -3/4. And then I'm going to do one other thing that's going to help us for some other parts of this question. We know 2 of the 3 sides of this right triangle. It's going to be helpful to us to know the third side as well. And now this is just going to be a Pythagorean theorem kind of deal. Let's do the square root of 4 squared minus 3 squared. That's the square root of 16 minus 9. The square root of 7 is what the third side of that right triangle would be. And the reason why I wanted to know that is knowing the cosine of the angle and which quadrant it's in, now I can also say exactly what the sine of that angle is and what the tangent of that angle is. I'm going to write down the sine, and that'll be very helpful for us finding cosine of 2x, sine of 2x, and the tangent of 2x. All right, so the sine of this angle is going to be the ratio between its opposite leg and the hypotenuse. That's the square root of 7 over 4. And we have to make sure we tell whether that is supposed to be a positive value or a negative value. Well, in the third quadrant, the sine of an angle is always negative. So we know that the sine of this angle x, whatever that angle is, we don't know, but we know that the sine of that angle is negative square root of 7 over 4. Great. Now let's actually calculate these double angle trig values. Cosine of 2x. You have three ways to be able to find the cosine of twice an angle. You have a formula that just uses the cosine value of an angle. You have a formula that just uses the sine value of the angle, or you have one that kind of mixes the two. I'm going to try to show each of them throughout the course of this video. I'm just going to start this time with the one that uses only the cosine. We know the cosine of 2x is equal to 2 cosine squared of x minus 1. And so what we're going to do is we're just going to substitute the value of the cosine of angle x into this expression. Cosine of angle x is negative 3/4, correct? So I'm going to have 2 times negative 3/4 squared minus 1. From here, it's just can you work with fractions more or less to get the right answer, and hopefully hopefully you are able to work with fractions pretty well here. If you square negative 3/4, you're of course going to get 9/16. I'm going to do a little mental math here. I'm going to do some canceling, then some mental math. When we're multiplying 2 times 9/16, of course, we can cancel the 2 with the 16, make that a 1 and 8 respectively. So we have really 9/8 minus 1, and that's 9/8 minus. All right, so you see we did a little bit of canceling there. 9/8 minus 1 is going to end up being 1/8. Voila. We know what the cosine of twice angle x is without even knowing what the value of x is. All right, let's do a similar thing with the sine of 2x. Now, there's only one double angle identity for sine, and that's the sine of twice an angle equals 2 times the sine of the angle times the cosine of the angle. And so here we're going to use both of those things then, the sine and the cosine of the angle. We said the sine of this angle has to be negative square root of 7 over 4. And we said the cosine of the angle, or we're told that the cosine of the angle is negative 3/4. Well, let's just go ahead and do the multiplication here, and we'll have the sine of twice that angle. All right, so we got a negative square root of 7 times negative 3 in the numerator. That's going to give us positive 3 square root of 7. And in the denominator, after canceling, we're left with 2 times 4, so 8. Now, I want to make sure that we understand whether or not these two answers are reasonable. And I want to remind you of something we did when we were solving equations with multiples of angles. This problem is telling me that x is between 180 and 360 degrees. In each of these problems, though, we're finding the cosine or sine of twice x. Well, if we know the boundaries for x, then we can double those to find out what the boundaries for 2x are. Now, where I'm going with this ultimately is I want you to understand whether the sine of 2x or cosine of 2x should be positive or negative based on the original angle. And it turns out just doubling the boundaries of x here didn't help me figure that out, because it could be anywhere between 360 and 720. You can have positive cosines and positive sines, negative cosines and negative sines from that range. But we actually narrowed down the range for x a little bit more because we said it had to be in the third quadrant. So x was actually between 180 degrees and 270 degrees, which means that 2x was between 360 degrees and 540 degrees. And so if 2x could have been anywhere from here to here, does it make sense that we got a positive cosine value for cosine of 2x? Well, sure, it turns out we could have gotten a positive value or a negative value there. Does it make sense we got a positive value for sine of 2x? Well, it turns out we had to, right? Because between 360 and 540 degrees, you only have positive sine values. All right, that's just a little added insight that doesn't necessarily affect the way that you do the problem. Okay, then the third part of this is we're finding out what the tangent of 2x is. And we already said that there does exist a formula for a double angle identity for a tangent, but we said you can just do sine of 2x divided by cosine of 2x. And since we know what each of those things are, because those are our answers for B and A respectively, we can go ahead and calculate the tangent of 2x. It's going to be equal to 3 squared of 7 over 8 divided by 1/8. Hopefully you've had enough experience with these complex fractions to know that when you divide a fraction by another and the denominators are equal, they end up canceling one another out, and you just get the top numerator over the bottom numerator. 3 squared of 7 over 1, or just 3 squared of 7, then, is the value of tangent of twice that angle x. All right, so pretty cool. That's how you calculate the sine, cosine, or tangent of twice an angle without a calculator and without knowing what the angle is. Let's try one more example. All right, this time I'm telling you what the tangent of an angle theta is, and I'm giving you enough information to hopefully figure out which quadrant the angle theta is. I'm telling you it has to be between negative pi over 2 and positive pi over 2. And we're going to calculate two things that are the same from the last example, cosine of 2 theta and sine of 2 theta, but then I'm also going to throw in the cosine of 4 theta. So you actually can find the cosine of 4 theta or 8 theta or something like that using double angle formulas, and I'm going to teach you how to do that with this problem. Let's go ahead and begin by making the triangle that shows where theta is. Now, between negative pi over 2 and positive pi over 2, we're talking in the fourth quadrants and the first quadrant, right? And in which of those quadrants do you have a tangent that is positive? Well, tangents that are positive occur in the first and third quadrant. Since our angle has to be in either the first or fourth quadrants, that means we're going to choose the first quadrant because that's the only one of those two that has positive tangent values. So let me draw a right triangle there. Let's just say this is the terminal side of our angle. We'll just put it somewhere in the first quadrant, and then we will connect it to the x-axis. Draw a line straight towards the x-axis to make your right triangle. And tangent, as you recall, in a right triangle, this is our angle theta, right? Tangent is equal to the ratio between the opposite leg and the adjacent leg. So we want to show that the ratio between the opposite leg and the adjacent leg from theta is 5 over 4. And while we're at it, let's go ahead and find out what the third side of a triangle with those two side lengths would be. In this case, we would do 4 squared plus 5 squared and then take the square root of that. That's 16 plus 25, 41. The square root of 41 is the hypotenuse. Now, as soon as you've drawn that picture, it's good practice to make sure you've written down the sine and cosine values for that angle if you don't already know them, and we don't here. We can now say that the sine of theta is going to be equal to 5 over the square root of 41. And that the cosine of theta is equal to 4 over the square root of 41. And because our angle theta is in the first quadrant, we know that each of those is supposed to be a positive value. You always have to make sure whether you should have a positive sine or cosine or a negative sine or cosine. All right. Now, cosine of 2 theta. We have 3 formulas again for that. We used the one involving cosine last time, so I'm going to use the one involving sine only this time. We're going to say that the cosine of 2 theta is equal to 1 minus 2 sine squared of theta, which means that it's equal to 1 minus 2 times 5 over the square root of 41 squared. All right, that's the sine of theta, and then we're squaring it. So let's do that math. Let's go ahead and do the squaring first. We'll have 25 over 41, and then a little mental math here. Hopefully we can handle that. This multiplication problem is going to give us 50 over 41, and we can think of this as 41 over 41. 41 over 41 minus 50 over 41 gives you negative 9 over 41. Now, does it make sense for the cosine of twice an angle to be negative if both the sine and cosine of that angle are positive? Well, think about this. If you have an angle in the first quadrant and you double it, can't that angle end up in the second quadrant? and that happens to be the case here, and if it does end up in the second quadrant after doubling, then it makes sense that it would have a negative cosine. Yes, that is possible. So there we go. Now let's use the same formula that we use for sine of 2 theta, because there's only one of them. We're going to do 2 sine theta cosine theta, and substitute. All right, and then the numerators, we're going to have 2 times 5 is 10, times 4 is 40. And then the square root of 41 times the square root of 41 in the denominator is going to give us 41. There's the sine of 2 theta. Now again, if we doubled that angle that was in the first quadrant, it had to either end up in the first or second quadrant, and both of those places have positive sine values. So we expected the sine of 2 theta to be positive. There we go. Our answer makes sense. All right, now I've given you double angle formulas, but I haven't given you a quadruple angle formula. And what I'm asking you to do is to find the cosine of 4 times the angle theta in this last little example. All right, well, if you think about this in the correct way, you're going to see that it's not all that difficult. A double angle formula helps you find the cosine or the sine of an angle if you know what the sine or cosine of half of that angle is, correct? Well, what is half of 4 theta? 2 theta, right? So really we can say that we're finding the cosine of twice 2 theta. And the reason why I'm pointing that out then is essentially we can use a double angle formula to find the cosine of what 4 times an angle is. And I'm going to use the last identity that we haven't used for a cosine double angle. We haven't used the one that uses both cosine and sine yet. That's that cosine squared theta minus sine squared theta equals cosine of 2 theta. Well, in this case, since we're finding cosine of 4 theta, we can say that cosine squared of 2 theta minus sine squared of 2 theta equals the cosine of 4 theta. And that means we can use our answers from the previous two parts in order to find out what the cosine of 4 theta is. Substitute the cosine of 2 theta and sine of 2 theta that you just got above. Now let's go and do the squaring. Negative 9 squared, of course, is 81. If you square 41, you get 1,681. Minus, and then 40 squared is 1,600. And that'll be over 1,681 as well. And then do the subtraction, you get negative 1,519. Negative 1,519 over 1,681. All right, looks like a ridiculous number, but it wasn't all that difficult to come up with, was it? All right, thank you. You now see how you can use double angle identities to calculate the cosine or sine or tangent of twice an angle measure without even having to know what that angle is. The next time, what we're going to do is we're going to be using these double angle identities in order to help us solve some trigonometric equations. As always, I appreciate what you guys are doing here. I appreciate the hard work and your attention to the video. Thank you. Good luck with all this.